video, I'm going to show you using plot xy how to produce a graphical solution of two equations. These methods are not used very much anymore because you have analytical ways to obtain a solution. But it will be useful if you want to get a quick estimate of your graphical solution. So we're going to start by looking at the solution of this equation, which is equivalent to plotting the left-hand side as a function f of x and the right-hand side as a function g of x, and then producing a plot of the intersection. What we're going to do, since I already defined my functions, I'm going to go here and insert a plot xy, and down below here I'm going to insert a system of equations where I'm going to put my f of x and my g of x. It's not showing much information, so I'm going to modify my vertical axis. Double click on it, and y I'm going to go from, let's see, just to try something, -10 to 10. So now, and also I get too crowded of a grid here in the y direction, so I'm going to change this to increments of 2. Okay, that's better. And so I obviously see an intersection here between 0 and 2 and 2.5. So what I'm going to do, I'm going to narrow down that area by going from 0 to 2.5 in x and going from 0 to, let's say, 6 in y. So in x, we're going to go from minimum of 0 to 2.5 in increments of 0.5. And in y, we're going to go from 0 to 6, we said, maximum of 6, minimum of 0, in increments of 2 also. So we're seeing some improvement in the solution there. It's a slightly larger than 4, and it's between 1.5 and 2. So I could proceed to narrow down my increments in x from 1.5 to 2, and say we're going to put increments of 0.25. Actually, 0.1 will go. And then for y, we see the intersection slightly above 4, so I'm going to put 3 to 5. And I'm going to make the grid in x a little bit finer and also in y, because I think I'm getting close to a solution here. So let's try 0.02, too many of them. 0.2, no. Let's try 0.05. Okay, that's better. And in the vertical direction, let's try 0.2. So we're seeing a solution there between 175 and 1.8 and 4 and 4.2. I could even narrow down to the 175 to 1.8. To narrow down my solution. I'm going to go even at like that value. And in the vertical direction, between 4 and 4.2. Right. I'm going to spread out this a little bit. I'm going to close here. So obviously I'm seeing a solution there around 1.7 is 1.78, I would say. And in Y is going to be 0.416. So let's assume that my solution, I'm going to call it x dot 0, and it's going to be 1.78. To verify that, I calculate f of x 0, 4.16, g of x 0, 4.19. So if I try 1.79, I'm getting too far away, so let's try 775, 0.450. So we're getting closer. So this could be a good estimate. Again, we're doing a graphical solution. There is no need for that. We could just simply say solve, copy the equation here. Actually, I'm going to type it. It's x raised to the square, space bar, plus 1, space bar, control equal, x cubed, x cubed, space bar, plus 2 times x minus 5 comma x equals. It turns out that the solution is 1.776. So we were close enough. But this is one possibility, at least giving you an estimate of your solution. As I mentioned, nowadays there is a lot of techniques like using solve here to obtain the exact solution, and so the graphical solution is just an auxiliary. I'm going to show you another example, and this is from hydraulics. And in this case, what we're trying to do is raise water from reservoir A to reservoir B using a pump P. The pump needs to provide a certain energy, which is measured by a head, H sub P, to overcome this difference of elevation, delta Z, from the lower to the higher reservoir by passing a discharge Q. There's a head loss here at the entrance, a head loss at the discharge, a head loss at the valve. The pipe has a diameter D and a roughness P and a length L. Here's the pump. Now, just ignore the background. I'm giving values here with the units separated. The units are all in units of the English system in this case. And that's because I used to teach at Utah State University, and in the U.S. they still use the English system, basically. Here's the sum of head losses. And for the pump has an equation which is a quadratic equation. And so it needs to do through experiments to find out what are the proper coefficients to use. Anyway, this is the way to calculate what's called the friction factor. It will give you an idea how much energy loss is lost in the pipe due to roughness of the pipe. In the end, I end up with two equations. One equation which is called the system equation that gives me the pump head in terms of the difference in elevation of the reservoirs, the discharge, gravity, the diameter of the pipe, the sum of minor losses, and the friction factor, which is a function of the roughness and the diameter. And this is called the Reynolds number, and it also is a function of L over D. This is equation 1. And equation 2, it's the pump equation. The function that gives the friction factor is given by this empirical equation. And so basically what I have is to solve these two equations simultaneously. So I create a function I call HP1 of Q, which is the system head, and HP2 of Q, which is the pump head. And so now I'm going to insert in here a plot, an XY plot, a system of equations where I'm going to put HP1 of Q, HP2 of, and what I'm getting there is a very narrow graph in there. So I need to modify my x-axis, and I'm going to go from a minimum of 0, that's a discharge 0, to a maximum of, let's say, 0.5. This is not showing much of a variation, so I'm going to make that x-axis even lower and go to 0.0, maximum 0.05 from 0 in increments of 0.01. Okay, so that's better. In terms of the head, however, let me check what I'm going to be getting if I use HP1 of 0.05, getting a head of 25. If I use HP2 of 0.005, I'm getting 1.5951. So I'm going to change my vertical axis to a maximum of, let's say, 30 and a minimum of 0. And the 30 is a little bit higher there, so I try 3. No, 3 is too small, so let's try 10. 10 is better. But I'm not getting my HP. Let's see. Actually, I finally got the curves. I have to paste again the graphic. And what I'm getting here, I'm getting close to the point of intersection, but I don't have enough vertical variation. So I'm going to change my y-axis to a maximum of 20. Let's see how far we go. Okay, that's better. And the increment here of 2. So there's my intersection right there. It's about 0.021. And I could say that my discharge for design Q0 is 0.021. The units are in for the discharge in cubic feet per second. That would be the standard unit. So if I try to find my heads for Q sub 0, HP1 for Q sub 0, I'm getting close, 1024 to 1019.021. In actuality, we could just use the solve function, and I'm going to actually go over here. But anyway, this is what I wanted to demonstrate, the graphical solution. And in the early years, this is the only way that you could find a solution with pretty good accuracy for the problem of pumping water between two reservoirs. Now we're going to do solve, Control C, Control V, Control equal to make it equal to the right hand side of this, comma, Q is the unknown, and we put the equal sign there. And it says, well, you have no real roots. I know that the solution should be close to 0.1. So in that case, I could put a comma here and let's say within 0 and 0.1. And that gives me my result. Now notice that I stay away from units here because units complicate things in here. And I'm going to give you another video showing how to handle units if you start with units. But if you can see the result, I'm getting 0.209. It's very close to the 0.01. If I change that to 0.209, then my two solutions here come even closer to the second decimal. And so this is another demonstration for a real practical problem of civil engineering, how you can use graphics to obtain an estimate of the solution for a particular problem. And that's what I wanted to present in this video.